So what is heuristics? Heuristic is a generic term that denotes an ad hoc intuitive role. So it's a function from states to numbers. It exactly knows what is going on in your search problem. It doesn't tell you what to do, it just tells you whether you are close to a goal or not. So it simply estimates how close a state to a goal. So what does it do? It looks at the state of the world and say, you are really far. In that case, it will return a big number. If you get closer to your goal, it will return a smaller number. So we can already imagine, I guess, how this is going to help us to a search. So let's look at an example. So in this problem, we have C3PO here. He's trying to find out where is R2D2. I need a general sense of whether or not I am close. How am I going to do that? Maybe we can use Manhattan distance. So, well, in order to reach R2D2, if I ignore all the walls, I have to go around 4 steps up and then 3 steps left. Maybe there is some walls in the way and I will have to go further, but more or less, if I am closer to the R2D2, Manhattan distance will be smaller. If I am far, in general, it will be bigger. What else I can use here? I can use Euclidean distance. It is not perfect again, but it is something. This is what heuristics are going to be. They won't be perfect, but they will be something. So if I move one step to right, up or left, if I go for example left here, the Euclidean distance will get bigger. So it means I am getting away from R2D2. So use domain knowledge. Are we getting close to the goal? Use a heuristic function that estimates how close a state is to the goal, and heuristic does not have to be perfect. What about for such problems? Okay, we understood if our problem is a distance between A to B, we can get straight line Manhattan or Euclidean distance and come up with heuristic functions. What about now? This is a 8 puzzle or n-queen puzzle, n-queen problem. There is a goal state and the wrong states. If you try to solve this problem with breadth first search, depth first search, or uniform cost search, let's say, we have to draw this search tree, and in that search tree for 8 puzzle there will be around 181,000 states. If it is 15 puzzles, there will be 1.33 trillion. If it is 24 puzzle, then 10 power 25, it is more atom than in the universe. So it is almost impossible to solve such problems. Then what are we going to do? We are going to use heuristic as people do. Let's create a heuristic for this problem. What it could be? What if we say, let's sum how many of them in the wrong place? Number tiles out of place. So we can see one is in the wrong place. So we are gonna let them to fly wherever they want. We are going to remove all the restrictions. And one will fly there and sit on the 2 tile. 2 is gonna fly and sit there. 4 is gonna just fly and sit there. So when we count all of them, how many are in the wrong place? 7 of them, only 3 in the right place. So heuristic here is 7. So it is very relaxed heuristics. We remove all the restrictions. Normally in the game you can move only the blank tile here. So you can move only to your neighbor. But in this heuristic we let them to fly wherever they want. What else we can do? Maybe we can just try to use stay with the boundaries and let them move to neighbors. In that case, it is going to be Manhattan distance. For example, 1 to go to its correct position, it has to go up one step. So this is 1. 2 is going to go on the right, 1. And 4, we can see it has to go first left, then go down 2 steps. So if we do the math here, the Manhattan, by using Manhattan distance, the heuristic 2 will be 10. What about our famous Romanian map? For such problems, we can use straight line distance. Our goal to reach Bucharest, we are in Arad and trying to find the shortest path to reach Bucharest. Here is the heuristic values, straight line distance values. In Bucharest, if you see the value 0, this is what we want, because when we reach the goal, we want heuristic is 0. From Arad, the distance, straight line distance is 366. After Arad, we have 1, 2, 3 possibilities. Sibiu 253, the heuristic straight line distance. Then Zerint 374 and Timisoara 329. Which one we are gonna pick? We see that if I go Sibiu, I am getting closer to the Bucharest. If I take Zerint, it is closer to me, but I am getting away from Bucharest. It means this is wrong to pick. But I am not sure after Sibiu if there is a road to Bucharest or not. We don't care. We are just seeing that if I go Sibiu, I am getting closer. So most probably I am on the right path. Now, what are we going to do with those information? How are we going to use these heuristics? So why don't we just follow the heuristics that we have done for uniform cost search? We were looking the costs and follow the cheapest one. In this case, we are going to follow the heuristics, and that algorithm will be called greedy search algorithm. Okay, let's say we are at Arad again and we are trying to reach the Bucharest, and we will follow the heuristic in some way. There will be still a fringe, and we are going to pick the cheapest heuristic from the Q fringe. We start with Arad. After Arad, we have 3 options. Sibiu seems like taking us closer to the Bucharest, so we are gonna pick that one. After Sibiu, we have 4 options. On the fringe, that is the closest, is Fagaras, because it makes immediate progress. However, the right answer is Râmnicu-Vâlcea. We go through Fagaras. Now the problem is, once we go through Fagaras, now we can see the goal, we can see the Bucharest. We are going to go straight there, and the good path that could be actually have been cheap, it didn't look good right away. And it is all on the fringe and waiting us to explore, and it will never happen because we reach 0 heuristic here. And we end up picking the high roads, and therefore we drive farther. That was the cheapest position. Let's have a look at another example about what can go wrong with greedy search. Let's say we are in city A and we are trying to reach the city B here. We check the neighbor cities, there are 2. We get the straight line distance, that still looks like better than the other one, so we will just go there. So after that city, we check again our fringe, there are 2 cities, and that looks like better than the previous this one, so it's gonna pick that one, our greedy search algorithm. If we keep going like that, the next one is closer, still this one is in our fringe, and keep going like this. We are doing a lot of ups and downs, we are visiting almost all the cities until we reach our goal. So what about this one? At the beginning we have seen that this is not in a good position, it is just taking you away from the goal. The greedy search will never pick this one. But unfortunately, we missed the shortest path. Instead of taking the highway, we took the countryside. And it took us to visit all the cities, restaurants. At the end, we reach our goal. This is what can go wrong with greedy search. Pros, it is simple, quick, easy to program, good for local search. The cons, it can take you straight to the wrong goal. It can get stuck in loops if no cycle checking, get stuck on local minimas and plateaus, and it is not optimal. Okay, checkpoint. I like you to give me the solution what greedy search is going to find for this graph, and you will assume that ties are broken alphabetically. These are the costs, you can ignore them. These are for uniform cost search. You are gonna take these heuristic values. You can pause the videos, take your time. I assume you did that one, and this is the path you are supposed to return with heuristic, with greedy search algorithm. It takes from A, D, because when we check, this is cheapest one. After D, there are two heuristics. That one is cheapest 4, then after 4. We found the goal. The heuristic is 0, so it will go with that path.